Today's video is going to be on CMake, looking at part 2 of installing targets. Let's get started. You just got to create a branch and get on with it. In my last video, we looked at CMake package configs for header-only libraries, which is a great starting point for what is necessary to go into getting targets exported properly. Now in this video, we're going to look at what is entailed to get compiled targets, such as shared libraries, static libraries, even executables, to get their exported target information installed so then a downstream consumer can use them. So when we create these CMake config files, we're looking at two properties to be important. One is we're designing the installed interface of a target. So when you build a target locally in a build directory, there's lots of properties associated with them, but there's a chance here to make the installed version of that target a little bit cleaner necessarily than what is done locally in the build directory. And then second, probably the most important thing we're going to focus on throughout all the topics of today is to make sure that these installed targets are relocatable. So we want to make sure that there are no hard-coded paths that end up in any of the properties on the targets we install. So when we build them and then install them, there's nothing from the build that is unusable from the install location, and that install location can just be moved around on the target system. So there are no assumptions built into where these targets are going to end up. So without further ado, let's start looking at code. Okay, so here we find ourselves looking at a project I have open. It's called RK-Common, which is a base library used in the Osprey build, so in the family of one API rendering toolkit projects. And it's nothing particularly special about the library itself, but it's got some CMake that we can use as an example to look at because it's a fairly small library, which is good. So in looking at this, it's a fairly straightforward CMake project, things you've seen before. You can find this up on GitHub, by the way, under Osprey/RK-Common. But before we actually look at the CMake, I'm going to open up a terminal and head over to a build directory. And I'll just clear this out. And I'm going to build it from scratch. I'm going to also do one other thing. Is I'm going to install it here locally under the build directory. I'm going to point it to and put it in install directory here, just so we can have a look at what are the contents that get installed here, so we know the products, the files, and what we're trying to end up with. We have that in our minds as we look at the CMake that populates it. So I'm going to go ahead and do a make install. Should make fairly quickly. It's going to build the test as well. And just like that, we have everything installed. So real quick, we'll see this is the list of everything that gets installed. So pretty obviously we have include headers. So all of the headers necessary to use RK-Common. And then, so that's listed last. We also have some CMake export files, the actual shared library itself. This is expressed as a shared library. And then we have the CMake config that if you go look at my video on demystifying find package, I'll put the link up here in this video for that. This is what we're trying to generate. So similar to last video when we did this for a header-only library, this time we're actually building and generating the CMake config file as a part of the build process versus a header-only library. It's possible to just generate to write this config file yourself and have it in the source dir. Obviously, it's up to you if you want to pre-generate that for header-only libraries, but we're definitely going to do that here for build shared object libraries. We got shared libraries, static libraries, executables. This is all the same for all of those. So we got to first look at installing these things, and then some other stuff we can do to get the target exports also in those export files. So the first thing I want to look at, before we do any install commands, there's an interesting note on relocatable targets. So I mentioned in the intro that we want to make sure targets are relocatable. That means that nothing that we build here in the build directory is actually installed, because if we look at like CMake current lister, CMake binary dir, these are paths that are specific to the build that I do. So if I open up a terminal here and I go to my RK common build, CMake binary dir is going to be this. So that means that if that got installed and then you downloaded a package that of a pre-built RK common and that path was in it, that would be a problem, because that path is only on my machine and we don't want to do that. So part of this process is making sure that these properties are divided between, at build time, what paths do we need, and at install time, what paths do we need. And there's only a few tweaks we have to do to make this, which is things called generator expressions, which there's documentation on what those are. They're very powerful. You can use them all over CMake. But for the sake of generating build versus install paths that end up on target properties, like include directories here that I have up, they're fairly simple and straightforward. So if we look here, target include directories public. Remember, for the basics of targets video, we talked about how there's public, private, and interface. And so all of these can have different build and install interfaces. Private doesn't make sense as much because the things that you're installing is already built. So private would only be at build time for that target only. But public and interface is necessary to specify here. So the generator expression is this syntax where enclosed in $ angle brackets, you have some type of condition that there's a bunch of different documented expressions that you can make. If this is satisfied, then the right-hand side of the colon is substituted there. So under build interface, we want to make sure that CMake current lister up one directory and that CMake binary dir are on the include path. So when we're just building RK common locally in the build directory, we want to make sure those are on the include path. However, on the install interface, we want to only publish the relative offset. We'll talk about this variable here in a sec, but we're only going to set it to the relative offset, which this ends up being CMake install prefix / include, which is, again, we'll get to that in a sec. But that's all this is doing. Otherwise, so it's as if this was specified at build time, and then that was called away on install and replaced with the bottom install interface substitution as well. And just so we're perfectly clear, the build and install interfaces, these generator expressions can be put anywhere. They are commonly mostly used for include directories because that's where paths really come into play. But because you have a include directory path that you're attaching to this target for downstream consumers to use. But however, any place that you need to use these generator expressions, feel free to use them. They're there to be used. So that's the basics of generator expressions to make sure we have things that are relocatable. So the next question is, what's the deal with CMake install include dir? And there's some more documentation on this that I can post here. It all comes into scope with including GNUInstallDirs. Now, I highly recommend this for basically every project that is a library that gets installed, is to just go ahead and use GNUInstallDirs because it's very cross-platform, it's very Windows friendly. At the end of the day, it just splits out. You have your binary directory in bin. You have your include directory structure under include. Lib has libraries, so .libs on Windows, and then .so and .a on Linux, and .dylib on Mac OS. And then there's other directories for other things that you can read in the documentation. But the key is that you'll have CMake install prefix and then those directories containing their relative items. And so when we look at install commands, CMake install include dir then has the place that include dirs are placed. What's interesting is this has a note then on packageability, because if we run CMake, hit advanced, you can actually let someone like a package manager who wants to build your project and offer it up in like a Linux distribution or something, that GNUInstallDirs helper module that you include lets these variables then be overwritable. So if for some Linux distributions like to not have lib but lib64, if anyone wants to have different places for all, so there's all kinds of listed locations here, libexe, cdir, localdir, all these things that big complicated projects that need all of these different items that they're generating need to go in the right places. But at the end of the day, you can inherit all of these for free. Of course, you could specify all of these yourself. You could go and just hand replace this with include instead of that variable name. But it's a good habit to start from the get-go to get used to using these when you're designing your installed version of your project. So go ahead and use GNUInstallDirs off the bat. It's pretty straightforward. You include this and those variables come into scope and become overwritable by people building your project. But now we got to actually install things. And so this ends up being split from like libraries into two different pieces. One is installing the target itself, which would be like the shared library, static library, your executable. And then and then in a separate install step, you install the actual target exports. So the target information. So there's installing the artifact the target builds, and then there's installing all the metadata, all that target information about that artifact. And so when you're doing a simple project, it can seem like it's a whole lot to do. If you wanted to, you could wrap this up in a little convenience function or convenience macro. But what this does is it allows you to design, when you install a target, you can establish where are the connection between the target information and the metadata about those targets. How are they organized? Because one thing we won't touch on today, but maybe in a future video, is components. Like remember in the video, if you go back and watch about find package, that there's ways you can specify like you want certain components. Well, all of these install commands and then the exported information about these targets all can be associated with specific components. So you can have a larger project with multiple targets being installed. You can put them in different components, but that'll be some detail you don't have to concentrate on for simple projects. So we'll leave that for another day. But if we look here at Arcade Common, there's two things. One is installing the target here, and then installing the exports. I'll go ahead and put some documentation up on the install command itself. I think there's plenty of details, and if you have questions, I think it's pretty well written about the things that you can do. Just remember all the way back at the beginning of the coding segment, we're looking to install a shared library and install the exports, the exported target information, and of course things like headers. So here, this is actually quite straightforward to say, hey, we're going to install libarccommon. We're going to give it a name for the export sets. So we can have more than one target that are all a part of the same group of exported information. And then the different library components, then like if you have a shared or static library, also depending on the platform, whether you're going to install, where you're going to install the library, runtime stuff. So like DLLs on Windows and then executables on all platforms, and archive, I believe, is static information. And then that's what this install command is establishing, is where do all these places go? And the CMake install libdir and bindir comes in from GNUInstallDirs. So this will actually physically put the shared library in the right place. And then this command, we linked, hey, we take everything that was installed in this export set, and we're going to put them in a particular export file. Now there's a default file name that would be this .cmake, and it's going to go in this destination. But you can also read the documentation on install export, because you can really configure a lot of different pieces about this. The one thing I'll mention is, remember also back in the find package video, namespace is where locally here we establish the name of this target without a namespace. That's kind of like its local representation. Then on install, it becomes rkcommon : and then the target name. So this would be rkcommon : rkcommon. So this is like the project, and then there's sub targets within the entire package that you're exporting. That's what that's doing. And remember, this is how find package, when you're on the consuming side, then knows, okay, yeah, this is an imported target because of that that namespace convention. Not required, but highly recommended for sane consumption to let other parts of CMake. One other note I'll say is about the destination for export files. The actual config itself goes under libdir, CMake, rkcommon dash, all of this. There's a set of directories that CMake find package will look for. Again, I'll cite, go have a look at all of the different places that you can put configs that CMake will look for by default. I highly recommend the libdir CMake project name. So this could be project name instead of rkcommon, then dash version. And what this does is, because you have the version information there, you could have, like, this is, I think, rkcommon 1.6 at the time. You could have different versions of rkcommon installed all in the same place, and then do a find package for a specific version, and they all could be next to each other, but because they're all exported correctly like this, you can use just one of them. So not a feature that matters to a lot of people, but like if you carefully craft this, kind of like this, then you can do interesting things like that. Now, one thing I'll note that I saw in the documentation that rkcommon hasn't implemented yet is this idea of a name link. So that's why you see a to install targets command, one where we skip name link, one when we this project has the name link. Then that's a thing on Unix platforms where you could say -l and then just a name of a library. And so what that is you can have a symlink from like the artlib rkcommon.so.1.6.0. You could have that, and then a symlink that's just lib rkcommon.so that points to it. So then -l rkcommon on the link line for like a non-CMake project would be able to just link rkcommon. Not a feature that's, I think, super important, because that only really matters when you want to have this like multiple versions installed next to each other type thing going on. But just wanted to say, hey, if you see name link, that's what you're trying to establish. And the CMake documentation on installing exports covers this. Last thing I'll mention on install commands is, yes, there's also ways to install headers. There's two different ways that I think are reasonable to do this. Of course, there's a bunch of ways that are outside of what I'm about to mention, and that's fine. It's your project. You design it how you want. But what I found helpful is if your project itself, like all of these headers, none of them are headers that I don't want to publish. So every single header in this whole rkcommon directory, kind of verbatim, I want to be installed under includedir rkcommon. And so what this means is you can actually use install directory command to match everything that looks like a header that you want to install. And it will then just take the whole directory with all those files that match and then just stick it on the destination. Really great thing. Works really well. If you don't want to have to worry about matching things, or if you want to have a selected list of what are your public headers versus non-public headers, I also recommend you can have just a dedicated include directory under your project, which Osprey does this. So all of the public headers are in one place, and then all of your internal headers are like this next to their CPP files. And then your install command is just the public header directory. So it's super simple. I guess you could also technically just install individual files if you don't have very many headers. All of those are valid approaches. The goal, though, is remember we're designing what ends up getting installed. So when you hit make install or CMake -- build the install target, when we make install, we want to make sure that list of things that gets copied into CMake install prefix is only the things necessary that we want to make sure it's a clean cutoff from the build directory. Okay, so you will notice that if you install these things, you actually don't get the config itself. So if we go and have a look at all the files that get installed here, if you were following along in your project, we haven't actually generated the config or the version config. You actually only get this exports file, which is only part of the equation. So the goal here is now that we have all this export information created, we need to create the config that brings in those exports. So when you do find package like rkcommon or find package your project, you get you satisfy the find package stuff with the config, and then the config brings in all of the exports. So that's the last thing I think we have to accomplish to have everything covered. So the way I typically do this is normal CMake list where each target installs itself, like installing the target and the exports accordingly. And then there's this lovely helper module called CMake package config helpers that you can include. And it brings in two functions that are really helpful. Configure package config file and write basic package version file. Of course, there's documentation, lovely documentation that can do this. But what this is doing is making it easy to have CMake generate some of the stuff that is necessary to make a config file that CMake likes. Now, the way we do this is it ends up processing an input file that has some stuff that gets substituted. And if you've ever done file configuration where you take an input CMake file and it outputs like an output file with substituted CMake variables, that's what this is doing. But it's specifically tailored for find package configs. And so the simple syntax is we say the input file we're going to generate, and then we put it in a destination. Now, interestingly, you could put this in your binary dir as like a local staging step, and then go ahead and install it. I highly recommend that for the sake of cleanliness, of dividing between because if you do this will end up writing, I think, to this destination on build. And then if you go through an install command like this won't happen until you do make install. So this is how you get that two-stage. But again, you design what you want to design. I would personally find it surprising if this went straight to CMake install prefix. So I very highly recommend using install files, but this is what this is doing is you take the input file, generate the output config.cmake, and then you do call out though on configuration, where is this going to go? So then where's this CMake config going to end up? And I basically almost always stick it in the same CMake config package config directory, just like we put the exports in. We're just putting it all in the same place. And so then that generates this file that we then install. Cool. Let's actually look at what is in that file. It's fairly simple. Now, without looking at some of this stuff down here, it mostly is you have this special package in it, and this @ syntax is what CMake uses to substitute that with things that it's generating from that function that I just showed you. So what we do is say, hey, we're going to include some stuff. We'll let CMake write some stuff in this file. Then the CMake exports that we want, I use project name, just like we did with generating some of these targets. What this is going to be is, hey, we're going to take the file that we specify that this install command creates, and we're just going to include it. So remember, find package is going to look for this config and then try to make sure that everything is satisfied to make sure the targets that rkcommon exports come into being. And that's these exports. So we're just including stuff generated by CMake that represents the installed version of RKCommon export information. So the target info, that RKCommon : RKCommon comes in this file. And then you could put just check required components, and that would largely be it. All this other stuff is actually specific to RKCommon itself. I don't want to spend too much time on that. I'd say the one thing here is that RKCommon depends on TBB. So that's what this is doing, is saying, hey, what like threading tasking system was RKCommon going, what was it built with? So that's what you're going to consume downstream. That is all extra stuff. And that's going to be a separate video, because there's a whole lot of interesting things to do with making sure you can find dependencies. But this is where we would do it. In this RKCommon config, this is where we would put information to make sure when we're finding RKCommon, we can find any other targets necessary, either on the system or we installed it ourselves, to make sure RKCommon : RKCommon works. That's the whole mission of this config, is to accomplish that. We touched a little bit on that in the find package configs files for header-only libraries, because NanoRT had some find dependencies in there for like OpenMP and whatever. But I think in a future video, I want to look at Osprey that has a lot of these, and it does it in a nice systematic way to handle downstream dependency finding from the find package config. So we'll get there. We'll get there. But if you're looking for the minimum ingredients, it's package init, include some exports, check required components. Should be good to go. What about this basic package, write basic package version file? Now that's a mouthful. What that is this is the specific file aimed at encapsulating the version information. So the config itself is like get the targets, and then this config version file that find package is looking for is what says, hey, this is the version we need. And this is where you encode the compatibility between versions. And so I think it mostly sticks with semantic versioning. So major.minor.patch. There might be another one in there. But at the end of the day, the version that's specified up here in your project could do this manually. I like doing it through the project command. So then that means this project, everything, you can just get a generic version. But at the end of the day, this is what ends up here. And you're saying this is 1.6.0 of RKCommon, and it is compatible with the same major version of other versions of RKCommon. Whew, so that feels like it's a lot. But the cool thing is once you get the mechanics of, hey, we're going to install our targets in the right place. We're going to install the exported target information metadata in an export set. It's going to end up in an export file. And then we're going to make a config file that includes those exports. That's largely it. So all the include DIRs, the preprocessor macros, dependent libraries, all that stuff that's a lot of mechanical things to package into a library target, maybe even an executable target, depending on what your project is. All that stuff is handled with these steps. So then when you do make install, you have now, if you've followed along, have just enabled your project to export that information so someone else can do find package like RKCommon, and then link the RKCommon target, and all that stuff that we built here locally got installed correctly and therefore could be consumed by them. So we'll leave it there for today. There's a lot of separate steps that go into properly installing targets themselves. So executables and libraries, and then the actual metadata as target exports. But I think if you go and you just look at each piece of the puzzle for the final install package that you're designing, that it's not too bad. And then what you have then is knowledge to scale that up to larger projects, include components, and do all kinds of fancy things to make a nice, clean, installed package of your project so people can robustly consume it. This is definitely something that can make or break the ease of use of a project. When you have a nice, clean installation of a library, big project, it can really go a long way to help your users get to using your library instead of figuring out how to import it. If you enjoyed today's video, please consider liking and subscribing down below, and leave a comment and let me know how CMake is going for you. If you're enjoying it, if you're having issues, let me know what you would like to hear about more. It's fun and encouraging to hear from you, and love to keep working on my own skills with programming and CMake and C++, as you are too. We're all in this together. So until next time, happy coding, everyone.